We're going to talk about some critical numbers. Critical numbers are X values. They're X values when certain things are true. So let's say that f is a function and it is defined at c, so it has a y value. If f prime of c equals 0, or if f is not differentiable at x equals c, then x equals c is a critical number of f. So we're going to look all through these two graphs and find all of the critical numbers. Okay. We're looking for where is our graph not differentiable, or where is the derivative 0. Okay. Straight lines are differentiable, differentiable. Their slope f prime of x would be like -1 or something. Oh, we come across a point, a pointy point, a corner. At any corner or cusp, your function is not differentiable. So corners and cusps. Okay. So at x equals 1, we have a critical number. C would equal 1 in this case. Second graph, curve, all differentiable. Looks fantastic until we get all the way up to here. Because over here, all of the slopes of the tangent lines would be positive. Any tangent line we drew would have a positive slope. Any tangent line over here would have a negative slope. But sitting up here at the top of a curve, a tangent line would have a slope of 0. So f prime of whatever that x value is 0. The x value is 2. So x equals 2 is a critical number. Over here, x equals 1 is a critical number. Okay, also called Cn sometimes, Cn for critical number. Okay. Relative extrema. Let's see if we can, on these two graphs, find relative extrema. So relative minimum or relative maximum. Whoa, looky right there. That lowest point, which is a corner, and it's also a critical number, is where our minimum is. It is a relative min. It also, in this graph, happens to be our absolute or global minimum. So our minimum is at the y value, which is more like y equals 0.3 or something like that, y equals 0.4. So f of 1 would be like 0.4, and that would be your relative or extreme minimum, relative and extreme minimum. Over here, min or max, all the way up here at the top is a maximum. So our maximum is at the y value, which is 1. So the y value of 1 is the relative, and in this case, the absolute maximum. Relative / absolute max is 1, and it happens at x equals 2. Over here, the relative / absolute minimum was like 0.4, and it happens at x equals 1. Okay. Relative extrema, those mins and maxes, can only occur at critical numbers. They're super special. They can only occur at critical numbers. It is not a requirement that a critical number will always have a relative min or relative max. That is super important because it is totally possible that you will not have a relative min or max. See if you can draw something that would be pointy and sharp, but would still not have a relative min or max. Or something where your derivative equals 0, but there's not a relative min or max. It's not as common for these things, but it is totally possible. So we're going to write ourselves a little note on that. I'm going to put it in pink to make it super obvious. Not all critical numbers will have extrema. Not all critical numbers will have extrema. I'm going to make that an exclamation. That's super important. Okay. However, if f has a relative minimum or a maximum at x equals c, then C is a critical number of F. So if you are told that x equals 4 has a relative minimum, you know that x equals 4. 4 is a critical number of F. Okay, but it does not go backwards. If it's a critical number, it might have an extrema. If it's an extrema, it is a critical number. All right, just make sure you keep really straight which ones are the x's and which ones are the y's. Critical numbers are x's, extrema are y's. Let's keep going. Find extrema on a closed interval. The absolute maximum or minimum, write that backwards, of a function will be found at either critical numbers or the endpoints of the interval. Hey, looky there. We might have endpoints being extrema. And we saw that on the previous page. We saw that there was a minimum here at an endpoint, and we saw a minimum here and here. So it's totally possible that endpoints will give you absolute mins or maxes. We also had that on some previous problems where we did acceleration, like find the maximum acceleration. And we looked at some endpoints and in between. So make sure you check all values, every single critical number and every endpoint. Okay. So this example, we're going to find the absolute max or min of f of x equals 3x to the fourth minus 4x cubed on the interval -1 to 2. We want to see where does f prime of whatever equal 0. So let's find f prime of x and then set it equal to 0. F prime of x is 12x cubed minus 12x squared. Alrighty, we're going to set that equal to 0. 0 equals, let's factor this side. Looks like we can factor out a 12x squared, and we're left with x minus 1. Set each factor equal to 0. X squared equals 0. I mean, it's 12x squared, whatever. So x squared equals 0, which means x equals 0. Over here, x minus 1 equals 0, which means x equals -1. Both of these are critical numbers because we found these two numbers by setting our first derivative equal to 0, which means that if you graphed it, there would be a horizontal tangent line. Horizontal tangents have slope of 0. But not only do we have to test x equals 0 and x equals -1, we also have to test the endpoints. So I'm going to suggest that you write these out starting with your endpoints. We want to test out f of -1, which is an endpoint. Hey, look, it also has to be the first critical number. That's not very common that your endpoints will be a critical number, but sometimes it works out. So we're going to test out f of -1. That is also a critical number. I'm going to put that there. We have a critical number at x equals 0. And that's all our critical numbers. So our last endpoint is 2. So we need f of 2. Oh my gosh, that should be a +1. Like, of course, that's why it doesn't work. That's why it's not common. It's not even the correct thing on this one. Here we go. That should be x equals +1. Nobody interrupted me. Come on. I'm kidding. It's a video. That'd be kind of scary if somebody interrupted me. All right, f of -1, f of 0, f of 1, which was our critical number, and then f of 2 because 2 was an endpoint. Okay, so we test all of those. Plugging in 0, we get 0. Let's calculator this. Save ourselves some time. So I'm going to clear everything out, go to y equals 3x to the fourth minus 4x to the third. All of our numbers are whole numbers, so I'm just going to go to a table and see what we get. Okay, 0, 0, 1, -1. Oh my gosh, those ones and -1s are going to kill me. 2, 16. And I can scroll up and get -1, 7. So we can see a few spots. We know that our graph is at 7, 0, -1, and 16. If we graphed this, we would know that our graph is at -1, 7. Oh, is this the graph of this? Oh my gosh, reading. To the left is the graph of 3x to the fourth minus 4x cubed. Notice that the critical point 0 does not yield a relative maximum or minimum. So why is that? Critical numbers do not have to produce extrema. So there's something weird going on here. It's that weird thing where your graph like curves and just like freaks out for a second and then goes through anyway. The reason behind that is that if you factored this out, you would get the 0, x equals 0, with multiplicity that is odd. So your graph like touches and goes through. Anytime you have an even multiplicity, your graph will bounce. Anytime you have odd multiplicity, your graph will either just like go straight through or we'll do this weird little guy right here. Multiplicity of 1, your graph will just go straight through, which is what this little business is. Okay. Our maximum is 16. This is the absolute maximum. It is also a relative maximum. Every absolute is also relative because it is the tallest thing in its area and it's the tallest thing overall. This is endpoints, not arrows, because we have an interval with brackets on the end. So it is a closed interval. So this point, which is -1, 7, is a relative maximum. Oh, this is definitely not finished. So this is like 2-ish. Not drawn to scale. This point up here is 216. So this point, which is 216, is the absolute maximum and it's relative because it's the highest in its area. This point 1, -1 is an absolute min because there's nothing lower than it. It is also relative because it is the shortest thing in its area. And then we talked about how 0 is not the shortest thing in its area, and it's not the tallest thing in its area, and that's because it goes through. The graph runs through that x-axis right there. Okay. So here are all of the maxes and mins, and this one is neither. So my suggestion of how to write this, start with the furthest left endpoint and then write your critical numbers in order and then finish up with the last endpoint. Or do all your endpoints and then do all your critical numbers. Just don't forget the endpoints. All right, let's keep going. We've got find the absolute max and min of f of x equals this whole business on the interval of -1 to 3. So we definitely have to check negative what? We have to check 3, check for the y values of those. But we also need to find some critical numbers. How do you find critical numbers? You take the derivative, f prime of x equals, derivative of 2x is just 2, derivative of -3, x to the 2/3. Power rule, -3 times 2/3 is -2. X to the, subtract 1 from your exponent, 2/3 minus 3/3 is -1/3. Okay, well, let's rewrite this guy. F prime of x equals 2 minus 2 over the cube root of x. Now, if you set this guy equal to 0, we can solve this to try and get x by itself. Let's do that. Let's add that fraction to both sides. So we get 2 over the cube root of x equals 2. The number that makes this true is honestly if x just equals 1. but solving it out, you can divide both sides by 2 and then multiply both sides by the cube root of x. So dividing by 2, we get 1 over the cube root of x equals, divide by 2 is 1. And then multiply by that cube root, 1 equals the cube root of x. Cube both sides. Okay, we could have cubed both sides like way back here, but we didn't because, I don't know, I'm the one doing this. 1 equals just x. Cube root, you get what you're left with. So x equals 1 is a critical number. We have another issue though. We have a critical number every time f is not differentiable. So f is not differentiable when our original function was defined, but our derivative f prime is not defined. So this one has to be defined, this one has to be not defined. Defined means that if you plug in an x value, the whole problem messes up. You cannot find a y value or you cannot find a derivative. Okay, so it has to not work in this one, but when you plug it in here, it has to work. All right, let's try something out. If this denominator equals 0, then you're dividing a fraction by 0. You can't divide by 0, that's not allowed. So set every denominator equal to 0, and that'll help you out. So cube root of x equals 0. If you cube both sides, you get 0. So x equals 0 is also a critical number. We're going to check everything in order, starting with our endpoints. So f of -1, f of 0, f of 1, and f of 3. Using a calculator, we can get f of -1 is -5, f of 0 is 0, f of 1 is -1, and f of 3 is about -0.240. It's not very pretty because you're taking the cube root of 9, which 9 is not a perfect cube. Okay. Let's take a look at what is the absolute max and min. It does not ask for relatives. We only care about the very, very lowest point and the very, very highest point. The very lowest y value is 5, and the very highest y value is 0, because everything else is negative. So -5 is the absolute max. 0, remember y values. Oh, my goodness, that should say min. Absolute minimum is absolute max. There we go. All right, last one on this page. Find the absolute max and min of f of x equals cosine squared of x plus sine of x from 0 to 2 pi. All right. So this right here is the same thing as cosine of x squared plus sine of x. So don't think that it's x squared, it's cosine of x squared. So for us to take the derivative, we have to do a chain rule. The outside function is a 2, right, x squared, and then you take the derivative of the inside function. Let's do it. F prime of x equals 2 times, keep the inside, cosine of x, decrease your exponent by 1, so 2 becomes 1, times derivative of the inside function. Derivative of cosine is negative sine. I'm going to put the negative in front of the 2, and then here's sine, plus derivative of sine of x is positive cosine x. Okay. So we have our original function, we have its derivative. How do you find critical numbers? Set your derivative equal to 0. So this is 0 equals. Okay, we got to factor something. We got too many things. What's common is that we have a cosine of x in both of those pieces. So I'm going to write out cosine x times, we've got -2 sine of x plus 1. You find the x values by setting each factor equal to 0. So 0 equals cosine x, and 0 equals -2 sine x plus 1. The first one, we need to get x by itself, so we're looking for including 0, including 2 pi, and including everything in between. What are all of the x values where cosine x equals 0? That happens at pi over 2 and 3 pi over 2. So x equals pi over 2, 3 pi over 2. You could do like an cosine inverse of both sides, making sure that you're in radians, but then it would give you decimals in your calculator anyway. Use a unit circle, find where cosine equals 0. Over here, got to get sine x by itself. We got 2 sine x equals 1 and sine x equals 1/2. So again, we're looking between and including the numbers 0 through 2 pi. What x values make sine of x equal 1/2? What angles make sine of that angle equal 1/2? That would be root 3 over 2. Nope. We're looking for pi's. 1/2 for sine is when we got pi over 6. There we go, pi over 6. And 5 pi over 6. Hint, it's always going to be the same denominator when you're looking for these. All right, so we're going to test out all 4 of those and our endpoints, because you can't forget your endpoints. Super duper important. So we need f of 0. We need f of pi over 6. F of pi over 2. F of 5 pi over 6. F of 3 pi over 2. And f of 2 pi. Plug this in your calculator. Okay, it'll get you numbers instead of getting like square roots and stuff and trying to compare square roots and fractions and all that. That's kind of messy. So my recommendation, plug this into your calculator, and then you'll have to do that like y1 thing. You know what? Let's just do that together. Go to y equals. We've got cosine of x, parentheses, squared, because you got to make sure that it's not the x that's squared, it's the whole cosine that's squared, plus sine of x. Notice I'm in degrees mode from a different video, so I'm going to go to mode, down to radians, select, and quit out of that. All right, so here's my function. It's in y1, and we want to evaluate y1 at all of these different x values. You can't see any of that. We've got cosine of x in parentheses squared plus sine x. I'm in radians now. I went to mode to fix it. Great. So we want to plug in all of these x values. They have pi's in them. Your table does not give you x values that are pi's. So we're going to hit quit by hitting second and then mode to come back to our home screen. To plug in all of those values, you're going to go to vars. Vars is here. Click vars. Go to yvars is the menu that opens. Click yvars by hitting the right arrow key. And then you want number 1, which is function. Hit enter. y1 is what we just plugged this into. So I'm going to click y1. What number do we want to plug in for x? So you put parentheses, and then the number you want to plug in for x, and then another parentheses. If you don't do parentheses, it'll just multiply your equation times 0. It gets really messy and dumb. It doesn't work. So y1 of 0 is 1. F of 0 is 1. This basically just says f of 0. We're going to do that again. You can go back to vars, over to yvars, enter, parentheses, and type in pi over 6. And hit enter and get 1.25. I'm going to show you a little trick. If you hit up, you'll highlight that. And then you can just retype over other stuff so you don't have to hit that yvars thing so often. Pi over 2 gets you 1. 5 pi over 6, the insert key, maybe you've never done this one before, insert is on top of delete, so you'll hit second and then insert. when you're at the spot where you want to insert a number, hit a 5. So it's 5 pi over 6 is 1.25 again. I wonder what's going to happen when we do 3 pi over 2. So that's going to be a 3, that's a 2, negative 1. Ooh, all right, 2 pi is the last one. So it's 2 pi. Hover over a thing and hit delete to just delete the one item without clearing out the whole line. Hit enter and we're back at 1. Alrighty guys, here are all of our y values for all of our critical numbers and endpoints. We're looking for absolute maxes and mins. The very highest number is 1.25 for a y value, and that happens here and here. And the absolute minimum is -1, which is here. So absolute max is 1.25, and it happens at x equals pi over 6 and 5 pi over 6. Absolute min is the y value -1, and that happens at, can't see what I'm writing, at x equals 3 pi over 2. Absolute max is the y value at, and then these were the x values we plugged in. Absolute minimum is that y value -1, which happens at that x value that we plugged in.